Welcome to the Aerospace Advantage podcast. I'm your host, John Baum. Here on the Aerospace Advantage, we speak with leaders in the DoD, industry, and other subject matter experts to explore the intersection of strategy, operational concepts, technology, and policy when it comes to air and space power. So if you like learning about aerospace power, you are in the right place. Now, to our regular listeners, welcome back. And if it's your first time here, thank you so much for joining us. Now, as a reminder, if you like what you're hearing today, do us a favor and follow our show. Please give us a like and leave a comment so that we can keep charting the trajectories that matter to you most. Last week, we introduced you to some key thoughts regarding why the Air Force is getting really serious about pursuing a new class of autonomous combat aircraft. The Air Force needs to add a lot more combat capacity to its existing inventory of manned aircraft to help buy down risk in certain threat environments and work around key challenges like regenerating combat power faster than the training timeline required for a full-up combat pilot. And developing this level of autonomous aircraft is a hard challenge to say the least. Elements of this technology exist at various levels, but no one has put it together yet in an operational, combat-viable package. Unmanned aircraft flying today are either remotely piloted or are basically following a script. So what we're talking about here today is true autonomy, machine decision-making and learning towards an objective. So for the first episode, we looked at the imperative, why do we really need to look at increased autonomy? Today, we're going to look at better defining key terms and concepts. This is a hugely complex topic, and folks are tossing around words in a very loose way. So this is leading to a lot of confusion. We're going to try to level set the playing field over the next 40 minutes, and next week we're going to bring it all together on the third episode, translating what this all will mean in an operational context. So today our panel includes our very own Heather Penney.
Hey Slick, it's great to be back.
We also have Mike Paco Benitez, who works at Shield AI.
Hey Slick, nice to be here.
Also joining us today is Darcy of Heron Systems.
Hey Slick, excited for this.
We also have John Dowdy, who works aerospace issues at McKinsey.
Thanks, Slick. Great to be part of such an illustrious panel today.
All right, Heather, let's get started with you. You wrote a report this year on this very issue we're here to discuss, helping normalize the understanding when it comes to the various terms, concepts, and standards when it comes to autonomy. So can you lay out the framework that you came up with for thinking about this complex topic?
Absolutely. So first, I need to give major credit to Major Chris Olson, who came to us from the Air Force Research Labs, where he was an engineer on Skyborg, which, as we all know, is one of AFRL's vanguard programs exploring how to create a core autonomy agent, right? That's the brains for autonomous aircraft. So as Chris and I were talking, it became very clear to us that policymakers treat autonomy like it's pixie dust. Sprinkle it on, it'll all be okay. And it was frustrating that there was a lack of understanding of what autonomy really meant, especially in the application of collaborative combat aircraft. So using the Society of Automotive Engineers levels of driving automation, this is really kind of how they break down a framework for, what we think of as autonomous cars, right? You hit the button on your Tesla and then sit back and let it drive you to work. And so we looked at that as a way to be able to create an understanding of autonomy for policymakers, for warfighters, and as a way that they could communicate with engineers. Now, granted, this is rudimentary, so there's a lot more nuances to it, but it was very useful in being able to get everyone on the same sheet of music. So if you think about the vertical axis as the levels of autonomy, right? At the very bottom, we consider that the least amount of autonomy. It's actually automation, right? Very deterministic, so the same input equals the same output. It's more traditional software programming, right? And then as you go up in those levels, you get to fully autonomous, which we understood as being the highest level of machine learning, adaptation, algorithms, right? Neural networks, because that really coincided with how warfighters and operators understood autonomy to mean. Now, you talk to an engineer, they look at autonomy and they go, it's a machine's ability to make independent decisions and actions. Well, if you think about it that way, my washing machine is autonomous because I program it, I hit the button, and it gives me the load and the clean laundry that I want. But that's not what operators understood as autonomy. So that's why we broke it down between the lowest level, deterministic programming, automation, the highest level, machine learning, autonomy. But understand that those are all layered as you go up and down. So you can have a mix, right? Now across the horizontal categories, we broke that down into aviate, navigate, and mission. Aviate is literally like that's how you're flying the airplane. That's your stick and rudder controls and throttle and engine and all that. Navigate is how you're getting from your initial point to your target, doing your route, you're getting your altitude, you're avoiding threats, you're not hitting other aircraft. But the mission part was really important. And the reason why we used aviate, navigate, and mission, where mission is the decisions you're making in the battle space, how you're managing your sensors, when and how you're maneuvering into a weapons envelope. That really mirrors combat pilots' cognitive functions, how we think in the battle space. And so we thought that was a really good model and a really good framework to get engineers and warfighters on the same page.
Now, John, you see aerospace from a number of different vantages. How do you see increased autonomy changing the marketplace and the notion of aviation at large? I mean, as far as I see it, we've undergone a huge shift regarding the definition of aerospace and aerospace professional. No longer we talk about folks who are driving in rivets. It's a huge game changer regarding the talents required and the scope of operational considerations, and a whole lot more, of course.
You're right, Slick. We're starting to see autonomy-driven shifts going on at multiple levels in the aviation markets. I thought maybe I'd try to point to two things that I think might end up being the most profound. The first one is a shift from hardware to software. I mean, aviation has historically been a platform-based business, and all of the processes, requirements definition, acquisition, test, sustainment, all of these things have their origins in buying hardware, and they aren't really very well suited to buying software. And make no mistake, autonomy is about software. The second thing that I see going on is a real proliferation, a re-democratization, if you will, of who can design and build an autonomous system. And that's manifesting itself in a couple of ways. Firstly, in the number of companies that can design and build autonomous aircraft, but equally the number of countries that have this kind of capability. And I think both of these shifts are going to be pretty profound. We're going to see a lot of challengers in the market to the more established players. And just like any time we're on the steep part of a learning curve with the introduction of a disruptive technology, I think we're in for a few surprises here.
Well, John, thanks. I appreciate that. I know it was a big topic, and I appreciate the thoughts on it. Any thoughts from anybody else?
I think that what John mentioned regarding the democratization of autonomy and what that enables not just non-big defense companies to be able to do, which I'm super excited about. It's great that we're bringing in new entrants because it's a fresh paradigm, fresh perspectives. And so I think that how that's going to expand the industrial base for the U.S. is phenomenal. Also, though, that democratization and proliferation of capability to other nations is something that the United States and the U.S. government needs to be far more aware of. So we have got to get way more serious about investments. We've got to get way more serious about buying usable prototype fleets and actually flying these in real live flies so that we can maintain that edge of technology that's going to be the crucial edge for military capability.
Yeah, and Heather, to expand upon that some, we look at it as a new entrant, right? One of those new suppliers that hopes to join this world. We look at it as also the way we design, build, and deploy this stuff is likely to mirror a lot more closely what we think of as a Silicon Valley or a big tech kind of approach to delivering software. So we believe fully that autonomy is going to be a living, breathing thing, and that it's going to evolve quickly, and that there's going to be this mutually dependent learning and then execution process that both the United States government and industry is going to have to engage in so that we can understand the realm of the possible in this new paradigm and rapidly drive toward combat effective capability. And for us, the best way to do that isn't to have a 5-year or 10-year long major program, but to structure programs in a way that align incentives so that we can do a fly, fix, fly, and then turn around and do a develop, verify, and field type cycle that ultimately gets this stuff into the warfighter's hands as quickly as we can.
Brett, I really loved how you mentioned that software cycle and how it's not going to mirror what we've done traditionally with hardware. I know that the DoD and the Air Force specifically has been looking to shift the way they do software acquisitions, shift the way they do software development. I mean, we've looked at software factories like Kessel Run. But when we begin to look at autonomous aircraft, that's going to challenge the way that we even operate and sustain and modernize these aircraft, a much more rapid cycle. So everything that you've talked about, I think, is not only crucially important for the service to be able to address today, but how they begin to think differently about that O&M cycle, that operational and maintenance cycle. And also, frankly, this gets kind of creepy, about the dollars, right? So this is going to require a major transformation across the entire Air Force.
And building on that one last point there, I would say there's another element when we think about how to deliver this, and it is what are the squadrons of the future going to look like? And we can get into when we talk about operations and maintenance and sustainment, we can think about, the contractual piece and the business models and things like that, and that's all well and good. But ultimately, I think how we think about collecting feedback from the field, collecting data and using it effectively needs to be considered very close when we're designing these programs. And I talk about aligning incentives. In Silicon Valley, user feedback and responding to user feedback either through, embedded, metrics collection or things like that, or direct surveying and going to your customers where they are, is looked at by the companies as being highly important to their product development cycle and something that they treat very seriously, and they kind of bend over backwards to do. For far too long and far too often, we can collect great data in the Department of Defense, but we don't necessarily apply it as part of a feedback loop. And if we don't do that here, we're really leaving, what I would argue is the majority of the value of adopting certainly machine learning technologies, but robotics technologies in general. We're just kind of leaving that behind if we don't close that feedback loop.
I'm laughing because in some ways you're addressing part of what my next report is going to talk about regarding teaming. So mission planning and then debriefing and being able to learn both from the humans providing that feedback to the autonomy, or even learning from the machine learning from the autonomous aircraft so that we can begin to develop and continue to evolve our own tactics. So I'm sure we'll have you back on when we're talking about our next report.
Looking forward to it.
All right, so let's transition a bit here. Paco, what's making autonomy in aircraft possible right now? We've dreamed of this for a long time. I mean, we're all kids when Star Wars came out and R2-D2 was flying with Luke Skywalker on the X-Wing fighter. So what's changed to make this within the realm of possible?
So it's funny that you mentioned Star Wars. So when Star Wars actually came out, there was nothing digital about that movie. It was all camera tricks and models. And the famous opening text crawl that you see in the beginning of the movies, that was done by dragging a camera across some printed out text on a piece of glass. So that was state of the art back then. But they could see and imagine the future. And if you start at Star Wars and kind of go forward, the world was slowly starting this shift from analog to digital. The term artificial intelligence actually dates to like the 1950s. So we've been thinking about it a long, long, long time. But a few things kind of poured rocket fuel onto this transformation to a digital world. Computers, data, and algorithms. So the first thing is, for computers, miniaturization. So some of us probably heard the term Moore's Law, which is about processing power. It's really about transistor density. And that states that about every 2 years, the amount of transistors that we can fit on a finite piece of silicon doubles. And that allows us to increase the processing power, and it allows us to build smaller chips to put in the things. And so today, there's a saying most people are familiar with, that a smartphone that you carry in your pocket is more powerful than the Apollo mission computer. I take that one step further. As of this year, a high-speed USB charger has more processing power now than the Apollo mission computer. So that's where we're at with the state of processing. And then when you process all that data, you need to store it somewhere. And so it took 51 years before hard drives reached the size of 1 terabyte. And that was back in about 2007. 2 years later, it doubled. 10 years later, it 10x'd. And so today you can buy a 20 terabyte hard drive and it costs about 4 cents a gigabyte, which is crazy. And the money matters because the economic models of processing and storage have completely changed. So if you go back to 1990, computing that used to cost $1 million now costs $100. The storage that used to cost $40,000 a gigabyte, again, costs about 4 cents a gigabyte. And then you take that with that changing in the computing and the processing, you have an emerging market, which was the gaming industry. And so in 1999, the first GPU hit the market. So your graphics processing unit, it's really good for computer graphics, but guess what? It's also really good for machine learning because they're really good at processing the deep neural frameworks that we have. So NVIDIA is probably one of the biggest one that's in that. So the gaming industry actually helped accelerate this. At the end of the day, though, those are all tools. What you really need is people to develop the software, the algorithms. And so those tools had led to the advancement of the body of knowledge to build that. And so now what we're seeing is the hyperscaling of neural networks and AI models. And so in the past probably 5 years, every 12 months, the size of the learning neural networks has tripled. So the largest one right now is by Google. It has about 1.6 trillion parameters. And that sounds like a lot, but there's a 100 trillion parameter language model that's actually being developed right now that'll probably be out in a couple of years. So the collective of the tools and our advancement of knowledge of how to build software with those tools is what's really accelerated autonomy.
Brett, hop in here. Do you agree with all that?
I absolutely do. And the thing I'd add to that, really the convergence where the hardware, software, and algorithms, and then I would argue networking too, because the ability to move data around between machines is kind of fundamental to all of this. That convergence really happened in the mid-2010s. So we're looking at probably 8 to 10 years since the first practitioners of what we would call, modern autonomy really had all of the capabilities in their toolkit to really seriously go after what we would call artificial intelligence today. And when I say artificial intelligence, I'm specifically thinking about the ability to reason over a complex space, right? So we can do things like solving Go or solving chess. It's not a very complex space at the end of the day. The board doesn't change that much, but something like a real-time world, common operating picture, something like that, that's going to change very rapidly in many, many different directions. And so we've really only had the ability to start to address that for about 8 to 10 years. And so what we've been doing since then is really building a lot of the foundational elements in engineering, processing, and tooling that allows us to tackle this. And simultaneously, we've been learning what works and what doesn't. For some of us, Heron Systems obviously included, we started as pure machine learning shop. We were doing neural networks and only neural networks, and that was it. And then at some point in time, we learned where the bounds were, and then how to overcome those limits. And we continue to progress. And so I say we're still in early days, but we're definitely entering the realm of the possible now. And so now our frontier is real world observation spaces, real world action spaces, and how do we take the thing that works very well in a computer and put it into a plane or a car and make it work. And that is the frontier that we tackle today. And we are in a similar learning phase for that, right? That poses a whole new set of challenges. We're going to build new tools, new techniques, new algorithms to handle that. But the good news is we have a lot to work with already.
Well, thanks, Brett. I appreciate that perspective. Any thoughts from the rest of the group?
I wanted to say another stark illustration of the power of Moore's law on computing. Paco, to your example about the lunar landing module and a phone being far too powerful an analogy today, it was my daughter's birthday yesterday, and the singing birthday card I sent her had more processing power than the computer on the lunar landing module. Compute has become disposable.
Okay, the rest of you are really familiar with Heather's report. It's been making its way around these circles a lot. What other core concepts did she hit upon that you think are key for folks entering this space? John, we'll get started with you, then Paco and Brett.
Great, thanks. I thought I might point to one thing I really liked about the report and one thing I was bemused by. So the thing that I really liked was that the framework, and Paco alluded to this earlier, like the one for autonomous vehicles from the Society of Automotive Engineering, is graduated. Autonomy is not binary. And I think part of the reason we get confused about it is people think about it as a switch, that something's either autonomous or it's not. But as the report points out, there can be different levels of human interaction and supervision. And I think that really helps people begin to understand autonomy at least a little bit better. The thing I was bemused by is that we need two different languages for warfighters and engineers. And I'll self-declare here, I'm an engineer. I think it's funny that we need a translator to connect these two communities. I'm sure it's true, but it's funny nonetheless. And for what it's worth, I think there's another community we all need to worry about. Sadly, I don't think that group speaks either of those two languages, and that's the general public and the court of public perception. And there's a lot of angst about autonomy, driven largely by popular culture from the Terminator on down. People have a dystopian view of AI and autonomy, and I think we're going to need to find a way to speak to that too. So Heather, there's another community to add into your engineer to warfighter translator.
Yeah, that's a great point, John. So when the paper came out back in February, I believe it was, I shared on social media, and the statement that I kind of tagged it with the link to the paper was, this is the most overlooked, underrated discussion of the year for Airpower. And I still believe that. And I'm glad to see what Mitchell's been doing to continually advance the discussions and being the thought leader in the space to really drive policy to where it needs to be and to drive the understanding where it needs to be. And so the paper, as John described, it describes a two-view framework. We spent some time earlier talking about the warfighter view, and it's really important we define that, because that is a fundamental part of trusting the equipment that you're given. So I think that was a great discussion, and a preponderance of the effort on the paper was focused on that, which is absolutely critical. The engineering view that John alluded to, I thought it's very nuanced, and it's a bit more complicated, and I think that Heather and Chris came to realize that when they wrote the paper. And so they focused on the things that we really need to focus on right now, which is kind of the warfighter's view. The reason I say that is why it's complicated is it really depends on the type of engineer. If you are an engineer that is in academic or consulting or in the government, you probably have a much different view than an engineer who's actually on a keyboard, like writing code for autonomy in industry for a company. And the reason is that the engineer who's working at a company, he's working on a unique software architecture complete with its own lexicon that fits their framework for their product that they're trying to sell. And so there's a language barrier just between companies based on the product. And I think that's more of a feature than a bug. Just the other day, we were doing a red team assessment of Skyborg's autonomy core system for the government. And even there, what the AFRL team calls a behavior is what we at Shield AI call a primitive. And we actually have a 5-level framework that we actually classify our types of behavior development through. So we talk about it through mission lens, a task lens, tactic, behaviors, and primitives. And then for us, that's critical from an engineering side. It allows us from the operator perspective to the engineers to have a discussion on each one of those particular blocks. And so we actually do speak the same language in our company between the engineering team and the operators. And so we talk about, you can point to a block and say, hey, what are we doing in that block? Do we need to randomize it? Or can we write a script for something that's already pretty much optimized? And so that lets our engineering team focus on their time and computing resources on the kind of the more reasoning and adaptation part of the behaviors.
So, Paco, I really love your discussion of that, because you're right. It is far more nuanced. And I think that's one of the things that's really unique about your culture there at Shield, is because you do have engineers and operators who are both savvy, and they do speak the same language. Whether or not your dialect is different, as you mentioned, like primitives and blocks and things like that, it doesn't really matter the language as long as you're both using that same language, and allows you to get those operational behavioral outcomes match, and then allow the engineers to be able to code and write to the proper level and do that functional decomposition to connect the software to the hardware and so forth. So I think that's a really good discussion. Thank you.
Yeah, and Heather, to build on that, the nuance I saw after looking at your paper is that there's a systems engineering challenge that we have to really wrap our brains around when we're thinking about delivering autonomy solutions that have a hope of becoming a trusted autonomous system as part of a CCA or what have you. And that is the entire system, from either the day in the life of both the human and the machine, has to be considered when we're thinking about everything about the solution. So that starts with the fundamental architecture of the autonomy. Does it support that day in the life fully or not? And if it doesn't, how are we thinking about communicating that and bounding the solution? But it also extends out to kind of pre-flight pieces, all the way back to the commanders who are going to authorize these things into combat. What does their mission planning look like? What reports do they have in hand that shows the capabilities and the current status of that autonomous system and its current evolution in terms of software updates? What do we have in terms of the ability to rehearse or otherwise use digital tooling to practice what we're doing before we make that decision making? What are we doing in terms of training to allow for the human to have confidence in his or her teammates, be them autonomous systems or otherwise, as we start to experiment with different tactics, techniques, and procedures? All that mission piece has to be considered, and we have to build this ecosystem. Really, it's not going to just be a piece of software that we put on a thumb drive and upload to a machine. It's going to be a very human-centric solution. And then we can see the other side of that systems engineering V, okay, so we've built the thing. Well, how do we go about verifying and validating and testing the performance in a way that both, creates trust, but also allows us to monitor continually progress against our objectives? If we hypothesize that this is an early days, kind of frontier level technology that we're going to bring and create an initial viable capability, and then we're going to rapidly learn, we must enable that rapid learning cycle. And it's going to not just be on the flight line in the field, it's going to be also back on the test ranges. And how we build the tooling to support that and link the test ranges to the laboratories, to the industry facilities and back is part of the overall solution that we have to engineer. And so it gets very complex, and far too often people are just constraining the problem to just what goes on the jet. And as a practitioner of this who works with operators every day, there's so much more than that.
So I know we've mentioned it a few times so far. Heather, you ultimately came up with a core framework as part of this report. Can you lay out what that is for our audience?
Absolutely. So we modeled our framework off of the Society of Automotive Engineers, who created a framework to help people understand and engineers understand autonomous driving vehicles. So using that as a starting point, because people are familiar with that, we then innovated and created something that we thought would be useful for warfighters, policymakers, and engineers. So I discussed previously that there are levels of autonomy, and here I'm not talking about just simply, the independence of a machine to be able to act, but how deterministic is the programming. So we call that automation. So very fixed, similar, same inputs, same outputs, very much like that ATM, or oftentimes I've heard people talk about washing machines. My washing machine is autonomous. Really, it's automated, right? I program it, I hit go, and I know what the outcome is going to be. So at that very bottom level, we have something that's very automated, so it's deterministic. And then there are levels that you can go up to you have like fully autonomous. So we conceptualize that as being dominantly machine learning with neural networks. And then, so if you think about those levels being in the vertical axis, categories were aviate, navigate, and mission. So aviate would be those flight control inputs to just literally fly the airplane. Navigate would be how does it manage around its environment through the battle space? So literally going from point A to point B, what altitude, what routing, how to do threat avoidance, and so forth. And then mission was that catch-all for everything from sensor management to how they employed weapons and the decision cycle process of influencing and controlling the navigation and the aviation elements to be able to execute those missions.
Okay, Paco, how do you think about autonomy's role from an effects perspective? And by that, I mean looking at it in terms of the outcomes we want to see. I'm guessing it's important to let the autonomy decide how best to get there and understand it might look different than human thinking.
Well, Slick, as an operator at heart, the language that the engineers and I use when we discuss this is optimization. And I think it aligns nicely because it's an outcome-focused approach. For example, and this is kind of the framework that we use when we talk to our engineers, given a mission, commander's intent, priorities, acceptable level of risk, and a finite resources, optimized to complete the mission. And so all of those feed into this model. And it's no coincidence, that's exactly what we do with humans. And so there's a certain amount of information that's provided so they can start planning to maximize the probability of success. But it can't just be that it's effective tactical autonomy based on the outcomes. It has to be trusted. And Brett had talked about that a little bit earlier. And so the behaviors, they do learn, and depending on how your architecture is, it's not a black box. It's a very explainable way. And that kind of depends on the type of learning and the type of architecture. And so that's when you get into machine learning. And so you have supervised, unsupervised, and reinforcement learning. And I know Brett or John can jump in here to discuss a little bit more if they want. But supervised is kind of task driven. Unsupervised is data driven. So we need a lot of data. And then reinforcement is based on mistake driven. And so you have kind of sticks and carrots, rewards and punishments to reward what you want to reward to incentivize, and then to disincentivize behaviors you don't want it to do. And what's interesting about the reinforcement learning is that it permits bounding of a problem to a way it can be very safe. So think aviate, navigate, but it also allows the behavior to explore the space to find some novel ways to complete its optimizations that we had not considered. And the way that Shield AI breaks it down is we can show you where the black boxes are, and we can control the inputs and outputs of that in a way that it becomes a very trusted part of our autonomy architecture.
All right, Brett, how does what Paco outlined, this optimization, differ from how humans would approach a task? And as you think about it, how do you see it from both strengths and weaknesses perspective?
Thanks, Slick. Paco's discussion about the different types of learning is important here because when we think about human learning, ultimately, the way humans think about something and execute something very complex is ultimately a byproduct of many, many years of learning, many years of training for the specific task, with a sprinkle of human intuition that we're going to pull from other life experiences outside of the direct training we went through in order to inform how we perform. So that's very different than how a machine is going to be built, deployed, and used, right? So when we use learning, even if we're using, bleeding edge reinforcement learning and lots of fancy techniques that excite engineers, ultimately, if that machine has not experienced the world in some way, shape, or form as it's being presented to it, it's not going to just pull things out. It's not going to make things up. It's not going to be able to take other of that machine's experiences that aren't directly in this kind of system and apply it. So you lose that element of kind of serendipity that comes from your general life experience or the general experience of the system. Like even if we build and deploy a system that operates extremely well in combat, if we lack that feedback loop from the sorties being flown either by that own system or its twin systems writ large, there's no learning that's going to happen at that point in time, right? Whereas a human, we fly a mission, we directly learn from that mission every single time and very quickly. And machines just don't perform like that. And so we have to understand kind of like our working model has to be very data driven, very data centric, because lacking direct injection of data and a training process that leverages that data, be it mission created, synthetic, or human input, we're not going to get learning and feedback. So we don't get evolution like we would from a human. And that could be a strength or it can be a weakness depending on how you think about it. One of the main strengths of machines, if they're built well, is they execute pretty much the same way every single time, and we can learn to rely upon them. And then we can adapt using the strengths of the human brain, right? Our flexible thinking and intuition. We can be the adaptive layer that applies that machine and sets it up for success. Think a construction worker using very simple tools to create very beautiful pieces or parts of a building. We can similarly do that as a warfighter. However, we're not going to get much more out of the tool than what we put into it. So if the tool is very simple, there will be limitations to it. We must understand that. And so ultimately for me, this becomes a question of how are we bounding the problem and setting up the machine or the autonomy for success, and then working within those bounds and giving ourselves permissions as engineers and designers and as warfighters and commanders to apply the tools effectively. When we're used to warfighters they're human pilots, I think we tend to get away with a lot more flexible thinking and optionality when it comes to mission planning and things like that. With the machines, we're likely in the early days to be much more constrained in that regard and relying upon the humans to work within those constraints.
Now, is it fair to say that humans and autonomy-enabled machines may be highly complementary, with their respective advantages and limiting factors melding into something that could be far stronger than either one alone? John, maybe you can take a run at that idea for us.
Well, I think complementary is the right term. I mean, many people make the mistake that artificial intelligence means artificial human intelligence. And Brett was alluding to this just now. They completely miss out on the fact that people and computers are good at different things. People are good at dealing with uncertainty and operating outside of known parameters and making judgment-based decisions where there is no rule or heuristic, no prior experience. Computers are good at totally different things. They're good at handling large data sets, about rapid processing information, about crunching through numbers, and about recognizing patterns in huge data sets. So assigning the computer to do things that computers are good at and leaving the human to focus on things that humans are still and will likely be for some time uniquely good at is incredibly complementary. In fact, I might go a bit further and use a different word, which is synergistic. The combination of the two is greater than the sum of the parts.
It's funny you mentioned synergistic. So the example, I lived, if we want to continue the Star Wars analogy, I lived my life as an F-15E Wizzo, so the human version of R2-D2. And I did that for many, many years, and a lot of complex situations and complex missions. And I'll tell you that in my experience, a strong F-15E crew, so pilot and Wizzo, generally maintain situational awareness and a high level of performance longer in those increasingly stressing and complex situations than a single seat fighter does. But I say that to say that the weak link in the crew for an F-15E, whether it's the pilot or the Wizzo, can be a boat anchor for the entire formation. So there's definitely the synergistic capabilities of that. I lived it, again, as the human version of R2-D2. But I just want to go back and highlight the chess teaming from the Kasparov's law, which is that man-on-man teaming will beat machines every time. And that kind of underpins advanced chess from episode 1.
So, Paco, you just couldn't stay away from the jab, could you?
Hey, now. Yeah. Hey, I called myself R2-D2, so
I know you made being a Wizzo seem really cool. No, but I love the fact that John, both you and Paco talked about the man-machine teaming being synergistic, because I really think that is going to be the key. We will always need to have humans within the battle space up there at the edge, using their judgment, doing what humans are uniquely good at doing. But I think that once we are able to bring autonomous aircraft, those teammates, to the battle space with us, it's going to be really just a total game changer.
Yeah, and Heather, from the practitioner side, what we are actively experimenting with now is where does that communication and synergy ultimately live? Like, can we figure out when the human should be involved and place that requirement or constraint onto the solution we're designing so that we're setting everybody up for success, and then from that decision point, we can then devolve the requirements down into what's the best way to communicate. How do we break down the different, tactics or behaviors that we need the autonomous system to be able to perform? And then the whole kind of mission set can evolve from there. But identifying when the human is best and how they can set up the machine for the most amount of success is really, I think, the kind of linchpin, discovery we need to make here. And I think we're rapidly getting there as we continue to experiment. But that synergy is great in concept. It's just really hard to figure out exactly how to do it. And so when I talk about evolution over time and building and maintaining trust, ultimately, I think what that does is it's a reinforcing activity to create that synergy. And we do need to set these systems up to be capable of this.
Brett, you're absolutely right. I mean, what Paco talked about regarding the teaming between the front seater and the Wizzo, and how when they had that team going, when that partnership was tight, I mean, that's a real unbeatable formation, right? And so it's that teamwork, it's that partnering between the human and the machine that are going to be really crucial. And as you mentioned, that's something that has to get built into the autonomy, because how the human and the machine interact, and that is a give and take relationship, is going to have a significant impact on how the machine then runs the rest of its algorithms. It's going to have an impact on how the autonomy makes decisions and what its outcomes and behaviors are going to be. And so knowing that you guys are beginning to explore that space, there are examples that we've seen of trust and how we partner effectively in the battle space, and that really comes from human formations, whether or not that's inside the same cockpit like Paco in an F-15E, or whether or not that's how humans have collaborated with, and Paco brought up this in the last episode, the skinny wingman, right? Your missile. There are examples of what that give and take, what those relationships need to be, that we can begin to model and then iterate and innovate from as we begin to figure out how do we create this synergistic relationship within the battle space.
All right, as always, we're getting short on time, but I'd like to comment on the important challenges that we're going to need to overcome when it comes to acquiring, building, testing, and fielding autonomy-empowered combat aircraft. There's a lot there, I know, so Paco, please kick us off.
Sure thing. So if it wasn't clear by now, to get where we need to go, it's all about the sets and the reps. So it's critical that we accelerate what we're doing so we can build, measure, and learn, which will decrease our uncertainty volume and increase our confidence interval. So when we talk about maturing the tech is the first thing. So we have to get autonomy in the air. So there's some programs that we're working on to get that. We need a test infrastructure that is sufficient enough to get the sets and reps to mature the tech in the air. So I'd say that serious tech needs serious resourcing to do that. We're working on it. The second thing is maturing test. So getting early involvement in education in the test community, and that's developmental test, from design of experiments with autonomy to operational tests, which is how do I optimize the application and the integration of autonomy. Then we have to work on maturing trust. Again, getting more touch points with more operators. Even if that autonomy isn't ready to quite fly yet, it's still in test. There are ways, because this is a software-centric capability, that we can accelerate that trust factor and getting those more touch points with the operator. And the one thing I want to leave you with is where we can do that. If you go around at every fighter base in the Air Force right now, there's a big building with a lot of air conditioners, and it's got a lot of simulators in it. So there is a way that you can skip the airworthiness and live fly restrictions and jump right to the behaviors and agent interactions by putting them in the sim. We're in discussions with the Air Force about that right now, that we could put AI in the sims today to either create better sparring partners to make our human operators better, on a path to then flip it around and put those behaviors on the blue side and look at man-to-man teaming.
One thing I wanted to add into the mix here is that I think we've got some challenges driven by the fact that the technology is advancing so rapidly. And Brett, you talked about this earlier, and it appears that it's going to continue to do so. And what that means in practice is that our ability to field autonomous systems is starting to get out in front of our thinking about how we can use and control these systems on the battlefield. And this is introducing a myriad of legal, moral, and ethical issues to wrestle with here. And in my opinion, the current thinking is, well, it's a bit fanciful. And I think we're going to have to really wrestle some of this down, but it's probably a topic for another day rather than one for today's discussion.
Yeah, John, as a builder, I have to think about the legal, moral, ethical, and we just rely upon current policy and design systems with a heavy human on the loop feature, right? That the C2 link will be very human centric, which I think is a good thing, because when we think about acquiring and fielding autonomy, my working hypothesis is that we should be building to be very close to what humans expect today, which is very much an iterative step forward from fully manned aircraft, and starting to introduce in small steps the deviations that are going to occur between unmanned systems and manned systems, right? So human expected behaviors being much more preferential than unexpected but effective behaviors when we think about trust, in building systems in that regard. And then working with the test community and the operating community to show them rather than tell them what autonomy can do. So there's a very major, we've discussed briefly the need for a test fleet and the ability to fly, fix, fly. For me, that's a fundamental prerequisite for any serious acquisition activity to occur. If we do not live and breathe and experience the autonomy in live flight, we are not going to be confident in making those decisions. When I talk to folks inside the Pentagon or on test ranges, the biggest hurdle I have to overcome with them is getting them to understand what the realm of the possible is and what a real world constraint really looks like. They will alternatively hypothesize that the autonomy can do far more than it can, and there's much larger challenges to overcome than there really is in terms of how to work with these systems. Or they will assume that autonomy is basically a flying brick, and we have a problem with making sure that it's effective enough to be fieldable. And they'll say that in the same discussion. So lacking real world exposure and those reps that Paco was talking about, we really aren't going to have confidence in our decision making. And in my experience, lacking confidence means that the decisions just end up not being made.
I watched with utter fascination the Alpha Dogfight trials where your team from Heron Systems prevailed over the other AI-driven systems and indeed totally decimated the human pilot 5-0. And part of my fascination was driven by the fact that AI does strange and unpredictable things, as indeed yours did in the dogfight. Rather than following conventional wisdom and trying to get behind the adversary to gain an advantage, you flew straight at the adversary and then shot without missing. And we see this in a lot of different manifestations of AI and autonomy, that the computer finds a way to win that's not one that we had thought of or considered. And I think this creates a real challenge in building trust, because one of the aspects of trust is that something becomes, in a way, predictable. And the reason that autonomy can be so powerful is that it's not always predictable. So I'm with you. The way to build trust is through simulation, test, and repetition. But I expect we're going to have some surprises along the way.
John, I'm really glad you brought up that notion of unpredictability, because I think that that's going to be a key combat and operational advantage for us in the future. And so how we begin to familiarize warfighters with autonomy, get them to trust the autonomy, and then how do we begin to iterate on the machine learning, so adapting our own tactics to be able to accommodate the learning that the autonomy identifies for us and suggests for us, and then being able to take that adaptation and those surprising solutions to the real world battle space. That's going to be a critical advantage. And I think it will take us a little bit of time to be able to get there. But again, as Brett says, flying with these aircraft, getting them into the simulation with real warfighters is going to be crucial to it, because I would offer that the conversations about ethics are important for us to be able to address, but it's ultimately academic until we actually get these aircraft in the air when we're flying with them. And I would offer a really important ethical consideration is, what are the consequences if we don't field these aircraft? What are the consequences if we don't have autonomous teammates? And I would say it would be far more hazardous and harmful to our warfighters and to our nation if we fail this.
Yeah, Heather, I think that there's a good news story behind your insight there, which is that we have found in our ongoing development that if we assume that we have done the simulation to real transfer, right? So the idea of these kind of AI-empowered systems flying isn't a human historical event anymore. It is now just another Tuesday. Once we get to that point, what we found is that using things like virtual reality or even, modern trainers gives us those reps very quickly, and that humans are amazingly flexible creatures when it comes to learning to work with AI or advanced autonomy, and then beginning to anticipate and understand what that machine is going to do. It happens far faster than we would have hypothesized when we started working on our current set of programs. And that's a very good news story from my perspective, because it means that, yes, there are major programmatic challenges that we must solve in order to get autonomy flying. But once we do so, the rest of that kind of .mil PF piece is achievable using means that we already understand. And that I think means that there'll be hard work, but then there's an acceleration behind it that we can kind of anticipate and plan around.
Well, unfortunately, that is all the time we have for today. I cannot wait for the next episode. Everybody, thanks so much for being here today.
Thanks, Slick. See you next time.
Thanks so much. I'm always happy to join a group of people to talk about one of my very favorite topics, the implications of AI and autonomy for national security.
Thanks, Slick. Thanks, Heather. This is a fantastic discussion and one that I learned a ton from. So thank you very much for having me, and can't wait to do this again.
Gentlemen, thank you all. We'll see you later.
With that, I'd like to extend a big thank you to our guests for joining in today's discussion. I'd also like to extend a big thank you to our listeners for your continued support and for tuning in to today's show. If you like what you've heard today, don't forget to hit that like button and follow or subscribe to the Aerospace Advantage. You can also leave a comment to let us know what you think about our show or areas you think we should explore further. As always, you can join in on the conversation by following the Mitchell Institute on Twitter, Instagram, Facebook, or LinkedIn, and you can always find us at mitchellaerospacepower.org. Thanks again for joining us, and we'll see you next time. Stay safe and check 6.